Hi, everyone. Thank you for joining this session. Let's get started. So today we're going to talk about machine learning engineering and MLOps. And I'm hoping to give everyone a quick introduction to ML engineering career, the skill sets required, the learning path. And I hope you find this session useful. Let's get started. First of all, quick introduction to WeCloudData. Just so you know that we are a data science training academy. We do have an AI and machine learning engineering diploma program. This is a 6 months part-time program. And we focus on teaching deep learning, computer vision, natural language processing in the first semester of this program. And the second semester, we focus more on the MLOps, machine learning model deployment side. And the next cohort is starting in March 2023, just next month. One of the differentiators of WeCloudData's bootcamp, compared to the traditional online courses, college programs, and boot camps, I think WeCloudData not only offer very structured curriculum, but we also, help students build portfolio projects. I think any kind of programs you join nowadays, it will teach you how to build portfolio projects. WeCloudData also gives students, 6 months access to industry mentorship. So you'll be working with someone who's a data scientist, machine learning engineer. They will give you one-on-one support on, resume critique. They help you with mock interview and also help you prepare for interviews. WeCloudData also has the option for students to work on real client project. The real life project can help students fill the experience gap. If you previously don't work in machine learning or data science, and if you want to become a machine learning engineer, I think adding a few months of real client project experience is going to help you make your resume look a lot stronger, and you will be, more experienced from a hiring perspective. A little bit about the curriculum. So this is a 6 months program, and so it's 26 weeks in total. Real client project is optional. So this program is created for people who have full-time jobs. They can't really, take a full-time boot camp. In terms of the curriculum, we start by doing machine learning review. So the prerequisite is that you need to know Python really well. You need to be familiar with machine learning already. We have a pre-bootcamp preparation course if you are, not very strong in Python yet. So we can help you get prepared. And then we start introducing deep learning, and then students will need to complete 2 mini projects, computer vision and natural language processing. That's term 1. In the second term, the focus is on MLOps. So we spend a lot of time teaching students how to deploy models in containers, deploy that to the cloud, how to scale the infrastructure, and also how to do CI/CD for machine learning. We talk about packaging as well. So yeah, I'll share the curriculum at the end of this program if you're interested. And the student get access to real client project. 6 months after graduation from the program, we also offer one-on-one career mentoring for another 6 months. So in total, it's a package of 12 months, and we're hoping to help student make a successful career switch to machine learning engineering and MLOps in 12 months. All right, let's talk about MLOps and machine learning engineering. You're hearing this talk, probably you're curious about machine learning engineering. From our perspective, machine learning is, compared to data science, it's more specialized, right? A lot of data scientists do machine learning engineering as well. They're in machine learning engineering doing most of the data science stuff. But I think the data science field is getting more specialized because companies realize that, having data scientists who can do experimentation, working with Jupyter notebooks and tune models, that's not enough, right? A lot of the models, the goal is to get them into production so they can actually generate value, and it can be integrated into real life applications. So it's not just for, insight and analytics. It can be used on the product side as well. For example, if companies are building recommender systems, so you need models to be deployed, and needs to work at scale as well. So there are a lot of practical considerations when we work on modeling and deployment in production. So the recent trend shows that, it's definitely catching up, right? Machine learning engineering, MLOps are becoming more and more popular as more and more companies and startups, right, move towards, model deployment and also monitoring in production. If you look at the open source ecosystem, it's also growing rapidly, and you're going to see like new startups in MLOps and in ML engineering, every week. So it's definitely an exciting time to work in machine learning AI, and in the past few months you probably have seen a lot of excitement around ChatGPT, and I don't think every company will be able to do that because the cost of training these models are pretty high, and whether we can use that in production, is it really going to replace Google, beat Google? I don't think it's going to happen that soon. So I think before that happens, machine learning engineers are going to play a very important role, in AI strategy for a lot of the companies. And not everything can be automated, even though a lot of the things should be automated. Machine learning engineers' role, right, in AI. If you look at this diagram, which is provided by Google in one of the white paper, this is how people look at, or data scientists look at machine learning, traditionally, right? Because they're looking at a machine learning system from their angle. They think that the machine learning code base is probably the most important. It's the model, data preparation, model training, tuning code, because that's where data scientists and machine learning engineers spend majority of their time. But around, machine learning and in this ecosystem, there are actually a lot of other, practical considerations for a machine learning system to work, right? So this is how it looks like in reality, right? ML in production. The ML code base is usually very small, even though you may write a lot of code for experimentation purpose. But when you deploy the model in production, right, the model itself doesn't require a lot of code. But for your machine learning models to provide value in production, you probably need to deploy that and package the model, right? You need a serving infrastructure, which means you need to build some sort of scalable endpoints, right? The API, so it can be integrated into some other frameworks and systems. If you would like to continue your model to continuously generate prediction, so the data collection and the feature engineering pipeline are usually even more complex, because you need to do quality control, right? Garbage in, garbage out. I think this is something we all understand. So if your model takes a couple of hundred or even thousands of features, how do we make sure that all of those features that's used for generating prediction on an ongoing basis are always correctly and accurately prepared? That's a lot of data engineering work, actually, and machine learning engineers need to be involved in that as well. And sometimes you need to be able to visualize the model and interpret the model, right, to the business and product team as well, because if you can't really convince the product and business team to about the model performance, sometimes they just lack the confidence to leverage the model you built. And that can be a waste of time and effort. Actually, majority of the machine learning models don't go into production. Right? And I think the visualization and interpretation part is also, a very important aspect of it. And if we would like to do machine learning at scale, right, that means we probably need to manage a cluster of machines, like GPU instances and CPU instances, to do distributed model training. And sometimes it's the training that takes more resource, and sometimes it's the serving. If you maybe the model itself could be a logistic regression model, so it's quite simple, it's not very big, but you have a very popular service or product that, and there are hundreds of thousands of people using your platform at the same time, and your machine learning models need to constantly generate predictions. So it's the serving part that needs to be more scalable and to be more low latency, right? So how do we manage all of these compute resources? And you need resource management as well. You probably need to scale that to a Kubernetes cluster, but companies do that in different ways, right? And there's the process management, model deployed in production. You also need to monitor that, because anything, like, things could go wrong anytime. And you need to have a robust monitoring system so that when things go wrong, you'll be notified and we can fix the problem quickly. And also, you need to do some sort of root cause discoveries to understand which part of your ML pipeline caused the issue, right? And sometimes it may take you hours and even days to figure things out. So taking all of these into consideration, machine learning engineering or modeling in production is actually a big topic, and you need to know a lot of different things. And it's usually a teamwork, right? So having data scientists alone is not going to make it work. And it's a collective effort between among data engineers, machine learning engineers, data scientists, product managers, as well as software engineers and infrastructure platform team. All right. So in terms of the job market, I think ML engineers will definitely need to work like, you need to have the software engineering, mentality. You need to be able to write clean and, good code, right? So doing everything in Jupyter Notebook, it's good for experimentation, but I think ML engineers will need to be comfortable working with a proper, IDE, get very comfortable with writing Python script, right? And run Python script from the command line and also know how to automate these scripts. That's the bare minimum. So ideally, I think you need to know Python because it's one of the most popular, ML framework right now, like language for different ML frameworks. But some companies will use Java and use, C++. So when it comes to model packaging, I think ML engineers need to know how to package models in different ways so that it can, be leveraged in your production system. Because in a lot of companies, models can be trained by data scientists using Python, but when it gets deployed into production, the production programming language could be Java and C++, right? So what kind of format do we use to package the model? And there are different options as well. But I think first and foremost, you need to know at least one programming language, and you need to get really good with Python, right? Because PyTorch, some of the most popular ML libraries, they are available in Python. And depending on the focus of the ML engineer, some ML engineers will focus more on the model training and tuning side. So they essentially work more like a data scientist, right? The title is machine learning engineer. So in that case, I think, TensorFlow, PyTorch, and Apache Spark are some of the skills, you need to have, because you might be dealing with, large data sets. So you will probably want to use a distributed framework to train machine learning models. Spark ML might not be the best, right? But there are some other options out there. Spark is really good for data parallel processing problems. So a lot of times the data will need to be pre-processed using Spark and, PySpark data frame. So why don't we train a model in Spark ML? But there are also other options such as Ray and AnyScale. Right? So Ray.io is a pretty scalable approach to distributed, machine learning. And also, I think if you work more on the MLOps side, ML engineers will probably need to know, cloud computing, understand a little bit more about platform and, as a service, and know how to build APIs. So if you work with Python tool, then, Flask, fast API are something you will need to know. But these are probably not the most popular, right, web frameworks in production systems. So sometimes you may want to either leverage, platform as a service, such as, Amazon SageMaker, or you have to roll up your sleeve and write some Java code as well. ML models are usually deployed as an endpoint, right? And served through REST API. So you're not really building, a large-scale web application. So I think the big part is still the model training, tuning, and also packaging. But when you deploy that, make sure you know how to deploy models in a Docker container. So I think ML engineers and MLOps, experts will need to still be very comfortable with different tools. But at its core, it's still, about machine learning and how to scale that, and how to build the pipelines more efficiently. All right, so there are different, data jobs out there, right? And I think ML engineers work in a team. So they need to interact with data engineers and data scientists. So if you look at this diagram, right, let's start from the bottom. I strongly believe that ML engineers should not just work on modeling, right? Because I think they need to understand the end-to-end ML pipeline, which means where is data sourced from? And they need to care about automation as well. So understanding a little bit more about data engineering will definitely, pay off in the long run. So data is usually collected by data engineer from the source systems, and data gets ingested, into the data lake or data warehouse as raw data. Data engineers will be processing those data, right, and then creating the analytics data set. If you're dealing with structured data, there tend to be a lot of work there, doing the ELT, ETL, data engineers and creating analytics data. But if we're dealing with more like, unstructured text and image data, it's probably not that sophisticated. So I think ML engineers will need to be able to work with Apache Spark to process a lot of the raw text and image data. And on the left-hand side, you'll see that, data scientists, right, they are building machine learning models, doing PLCs. Models can be used for batch predictions, and the data engineers might be helping the data scientists automate their batch jobs. I'm not saying that data scientists should not be doing that, but in some teams, it's the data engineers who are building, data pipelines and automating ML models as well. But in some other companies, it's actually the ML engineers doing that. And data scientists will focus more on the experimentation side, right? And data scientists work more closely with the business, right? They're solving like ad hoc business challenges as well. So they work closely with the sales and marketing team, for example, to address, business questions and build predictive models. ML engineers tend to work more closely with the product manager because, you want the model to be deployed in real time, and that model got to be used by, your software, some other software team, and get integrated into your web application or mobile application, right? So ML engineers will be working on, deployment side, right? And work with MLOps or DevOps team to build the CI/CD pipelines and get the model deployed. And I think ML engineers care a lot more about the scalability, right, of your applications in production. So it's, you're leaving this, experimentation environment, and you want to deploy that as an actual software product. And the outcome or output will be used by the application team. So hopefully that helps you understand, the differences, among different data and ML roles. Okay, I have some practical advice for people who are doing machine learning and data science, right? Before we move on to talk about ML engineering and ML ops. So first of all, if you look at the ML lifecycle, right, or the entire end-to-end workflow, I think you understand that it usually starts from the business question, right? What are we trying to optimize? What is the objective of this machine learning project? And then data scientists and engineers will start to source data. Do we have the data, right, and labels to support this kind of business assumption to work on it? Is this feasible for this project? So of course they will need to start doing some small scale POC, extracting and preparing the data. And hopefully in some companies the data is directly available in the data warehouse. You just get to work with whatever that's available there. But in some other cases, I think data scientists and ML engineers will need to be involved in sourcing data if the data is not available, or sometimes it's the label that's not available. So how do we label the data? Right? You either work with a third-party vendor. Do you label the data yourself, or you leverage Amazon SageMaker? But there's always time and cost constraints as well. Right? But once you figure out the data part, right, or the data sources, we'll need to do data ingestion, right, extraction and pre-processing, and you'll need to do some data exploration and analysis. If you work as a data scientist in a more established team, I think you're probably going to be very familiar with the data already, right? Someone else, a senior data scientist, have built some models in the past already. You're just maintaining the model. But if you get to build like new models, you might be dealing with different kinds of data and some new data. set, which can be quite exciting. So you definitely start from data analysis and data exploration as well. And then we enter the model development stage, right? Model dev means that you're going to work with, for example, Jupyter Notebook, doing a lot of the interactive analysis. You start to build your base code, and you're going to fit some baseline models as well. And then when the code is developed, you're going to do model training. Now, if the modeling problem is not and not very big, let's say you're dealing with relatively small data, just training that directly, the model dev and training is probably the same. Happens at the same stage. But if you happen to be doing a lot of the image processing, or you're dealing with large scale data set, model training can happen in a distributed fashion on a cluster. So this includes the model tuning, hyperparameter tuning, right? So that is the expensive part. You may want to outsource that to tools like SageMaker, or your company may have a dedicated cluster for you to do model training. And then, of course, you want to do model validation, which is always a part of the model training process, but you may want to do model testing, right? And model analysis, and interpret the model results to the business. And if the model performance is acceptable and people like your model, you're moving on to the model deployment stage, right? Sometimes you're constrained for time. You're just going to build something quick and dirty, and you deploy that very quickly. And then you start to collect live response data. That's another approach, right? In some companies, model building and training state, and validation process may take months and months. But in some other companies, you may just build models really quickly, and you want to deploy that first, and so that you can start to leverage the model and keep iterating on it in production. And in that case, you're going to constantly update your model, right? Hoping to get fresh data, and by working with real data, you're able to improve the model performance iteratively. And then when the model is deployed in a live system, you're going to run into all kinds of problems, right? And sometimes, it's just not outputting the correct, prediction, or sometimes things break. And sometimes maybe, your application has a surge in traffic, and the model serving infrastructure is not able to keep up. So all kinds of production issues. This is where MLOps folks are going to, play an important part. So this is the overall end-to-end process, and of course, this is an iterative process, right? In production live system, when you run into issues, you probably need to come back. When you deploy the model and you notice that the model didn't really do very well in production, you may come back to model dev stage, or sometimes you realize that no matter what you try, you can't improve the model performance much. Then let's think about the data. Can we, start to implement some new features to collect more user behavioral data? So that means more data collection and ingestion, right? And you have to wait for the dev team to implement the changes, and then in the hope of collecting more data, and then you keep iterating on it, improve your model, right? The more data, the better, I would say. All right, so feedback loop is important as well. So let's talk about different stages. I skipped the data ingestion and data engineering analytics part. So let's talk about the model development. Some very small tips, right? It's a pretty big topic, so I just have one slide for each box here. First of all, I think at the model dev stage, before you jump into the model training and tuning stage, it's important to build a very simple baseline model, right? You're just validating some of your assumptions. And you can even use AutoML tools, right? Such as PyCaret, but there are a lot of AutoML libraries out there. They usually come in handy, and you can use that to build baseline model, or you can just, I think most of the data scientists and ML engineers have their own, libraries, so that they can reuse the models, code built in the past, and to train very quick and dirty models. And you just want to, for a new machine learning problem, you just want to tell that your model actually, will give you some, basic, performance, right? It's not going to look too bad. If the accuracy of the model is only 55%, you probably shouldn't really spend too much time on model tuning, because it probably means, something is wrong with the business logic, or something is wrong with the data or features. So you have to spend more time on that and figure out why. Or is it because it's a very hard problem, so you can't really get a very good performance? And then you have to do some research, right? Check out some of the industry, benchmark for similar problems. So building the baseline model, it doesn't take you a lot of time, but sometimes it's going to save you a lot of time. So that's something highly recommended. And of course, for model training and tuning, you need to understand cross-validation and also hyperparameter tuning, right? So this is just really a process for you to select the best, model. And machine learning is a bias and, just a trade-off between variance and bias, right? That's most of the effort we do, right, are actually built around this bias versus variance challenge. And just keep that in mind. And we're trying to build models that has low bias, but at the same time we have to balance the variance as well, because I think model running in production having low variance is always preferred. And then when we deploy the ML pipeline, definitely don't give a Jupyter notebook, right, to your developer or software engineering team. I know there are ML engineering platform out there that that actually choose like Jupyter notebook, but most of the time they actually have to extract the code and turn that into Python script. So it will, I think it's a good habit, right, for you to modularize your ML code, data loading, right, transformation, feature extraction, try to separate them. And the model training sometimes can happen on a different GPU instance. It doesn't really have to happen on the same machine that you use for data preparation and feature preparation, right? And these can be easily containerized. For example, if your company use Kubeflow, and you can actually separate these, building blocks and use different type of infrastructure to process each stage. So building this ML pipeline is very important. Even if you're just using scikit-learn, I think it's important for you to leverage, the pipeline feature, right? So you can standardize the data transformation and feature extraction process. And make sure that your training and test data set go through exactly the same ML pipeline, right? So that it has less bias and no bias when you're doing the validation. And model interpretation is very important. And a lot of times, model interpretation doesn't mean using very mathematical way of explaining that. Like I think for data scientists and ML engineers, using Shapley value makes a lot of sense. That helps you understand the model better, or understand why some models perform better. There are many different ways to do model interpretation, and there's packages such as Lime as well. But in practice, I found that if you're trying to interpret models to the business team and product team, sometimes doing very simple visualization can actually help. So you're doing some sort of post machine learning model profiling, right, to help the product team understand how your model performs, because they understand the customer features and attributes better if you're building customer churn models, for example. So try to apply your models, and generate prediction and use that to to interpret the model. And sometimes it's just pie chart, bar chart, and also line chart that can help you actually explain the model better in layman's term to the product team, so you get the buy-in from the business side. All right, and then on the machine learning deployment side, I think this is where machine learning engineers are going to play an important role in, and we talked about this, right? So modeling a model in production, there are a lot of other steps that are associated. So I think ML engineers need to understand automation, for example, understand how the data collection and engineering pipeline, and sometimes you need to include that in your ML engineering pipeline. And if your company is using some sort of feature store platform, that would be great, but ML engineers will probably work closely with the data engineers to maintain the feature store. And on the serving side, there are a lot of different options. And a lot of times you are actually involved in the high level architecture design or in the system design, right? Do we directly, translate the Python model into Java code, right? So you're building a more taking a more monolithic approach, or should we go with microservices approach, and you deploy models in many different API endpoints? And I think it depends on the goals and constraints, and you have to make the best decision. Do we deploy everything in Docker containers and host that on AWS? Or do we maybe just consider using Amazon API Gateway and Lambda functions? So we do this in a serverless fashion, right? But if we do this using Lambda function, it has a limitation as well. So if your model is too big, the cost may actually be really high because it requires more memory. Every function call will be more expensive. So, and you have to do some experimentation and benchmark to help the company make a good decision. And of course, in practice, sometimes you even need to go with a simpler model, maybe even just logistic regression. If you have tens of thousands of features and you have to generate prediction with really low latency for online advertising, for example, then you may as well just go with very simple model, because the model artifact is small and it takes less time to load the model. It generates prediction much faster. And all of these time saving, even just in tens of milliseconds, can make the infrastructure and system more scalable, and it can help the company even save more money, right? So there are a lot of software engineering consideration you need to put into your ML systems. And of course, when it comes to ML experimentation, right? When we build models and deploy that in production, you need to keep track of your modeling effort, right? A data scientist may build like 50 models and pick the best one to be deployed. Or a senior data scientist left the company and he built a super, performing model about 6 months ago, and now something goes wrong and you have to sort of just retrain the model. And he just realized that this person has left and you don't have his laptop and things are not saved in GitHub properly, right? And you don't have documentation, even if you have the code, but you don't have the same version of the data set that was used for training. So the biggest challenge at the very beginning was, well, how do we even replicate, the previous model, right? And so that you can, you have a good starting point, and then you know how to do optimization. So ML experiment tracking is also very important in production. So there are a lot of tools, and ML Flow is one of those tools that not only provides a tracking server, but it helps you to do model monitoring and deployment as well. When we deploy models, I think nowadays ML engineers all prefer to do that using Docker container. So you need to make your ML system more portable, right? So containerizing your pipeline is important. And I think that the challenge with model deployment in the past was that data scientists will be using Python and drip the notebook, and then they export the Python model. In a production system, the production server might be using a different version of Python, and maybe you're using TensorFlow 2, and the production server only has TensorFlow 1, and the Python version also has conflicts, and that's going to cause a lot of trouble. So the best way to do this is just to containerize your model pipeline, and so that people can replicate, reproduce the same environment in production container environment, so they don't have to worry about these dependencies, and that's very important. So that means ML engineers need to understand a little bit about Docker containers and Kubernetes and different kind of infrastructure as well in the cloud. And modularizing your pipeline also means that different parts of your ML pipeline can actually be processed using executed using different types of infrastructure, right, to optimize the cost. For example, the model training part, if it requires GPU instances, then maybe you just want the model training and tuning part to leverage the GPU cluster. and you don't want to leverage the GPU cluster to do, CPU intensive jobs such as data processing, feature engineering, right? It doesn't require GPU to do that. So you can save a lot of cost, but first of all, you need to modularize your code and pipeline as well, right? So, but this is actually easier said than done. You're probably going to need some sort of orchestration platform. If your company runs everything on, Kubernetes, then Kubeflow is one of those platforms that allows you to do this. If your company works with AWS, then you can leverage, SageMaker for that purpose. All right. So we just talked about, the machine learning process. What about MLOps, right? MLOps is more on the on the later half of your ML pipeline, right? We're talking about automation, deployment, packaging, right? Monitoring in production, and also scaling of your infrastructure. So this is a very good end-to-end ML ops architecture, overview. It's a paper published sometime last year, I believe. So I won't spend a ton of time on this, but just to give you a quick rundown of it. First of all, I think any kind of MLOps or machine learning engineering project starts from the project initiation. So you need to have the right team, right? So data engineers, data scientists will all be involved in this, but you're going to have the project managers and the business team as well, right? And then figure out the requirements for data, right? Feature engineering pipeline. And then that means, you're going to be working with data sources. Data can come in batch from databases and data lake, right? For example, cloud storage. But data can come in, in a streaming fashion. So you have real-time streaming data. Right? If you have streaming data, you would like to do real-time processing, feature engineering, then you need a different kind of infrastructure. You need Kafka and Spark Stream, for example. So there's the data pipeline, right? Or feature engineering pipeline that you need to take care of. And then once the data is ready, data scientists and data analysts will start to do experimentation, right? Data scientists will be doing some data analysis, as I said, right? Exploration, visualization, and then you start to build models. So model training and validation. This is usually iterative processing, and along the way, you want to save all of those experimentation, right? You want to tag those models for each model you built or each experiment you did. You would like to keep track of the source table and data, right? You want to like the version of the code and the model artifact. You want to keep track of all of this so that you can reproduce, those experimentation down the road if you need them, right? So this is where ML flow comes in, right? So you can set it up and, it's just a couple of more lines of code so you can start to track your models. And after the experimentation, and if you find a model is, there's one model that's doing really well, you want to save the model. So that's the model packaging part, right? You want to export the model, but in what format, right? If you're just pickling your model, the performance is not going to be very good in production because the model file is usually very big, right? So you don't compress the model very well, and the loading speed might be slow as well because it's just using Python, right? So there are better packaging, format that you can leverage, and then you save the model. Now, one of the differences between ML engineering and software engineering is that software engineers usually just care about the code base, right? But ML engineers not only care about the code that's used for model prediction, right? The model itself, the model artifact is also important. So you need to version control your model file as well, right? So the model artifact, you want to save it and version control that. So there's the model registry version control tool. There's also the data version control tool called DVC here as well. So when you work on MLOps, even if your company don't use these latest, open source tool, you're definitely going to touch on these, ideas, and you're just finding your own way of doing that or leverage existing, packages or libraries to do that. So of course, you're not only version controlling your data, ML pipeline, and also the model artifact, right? There's a little bit CI/CD here, right? You would like to, constantly update your model code base, and you probably want to do the continuous, integration and testing as well. And the deployment side is really just the deployment of a Docker container, right? That has your model artifact and everything, and then you would like to export that to your model or container registry. So up till this point, you finish your data science part, machine learning model training, where a model has been exported and saved in a model registry. The next step is model deployment in production, right? So you need a serving infrastructure. How do we serve the model? And this model serving in production also means that where do we get these real-time features from, right? If the features are automated by, like, for model training, you need a table or data, a data frame, for example, that has all of the features, and so rows and columns, right? Where do we store that? How frequently do we refresh that table, or do we refresh the table on the fly? So you probably need some sort of feature store. In a lot of the use cases, data engineers may automate a data pipeline to update, one of these feature tables and save that in the object store or in a data warehouse table somewhere, so that your model can leverage it. But if you're building more like real-time based system, you may want to leverage a NoSQL database for that purpose, right? And of course, you need to make sure that the data quality control and governance is in place, as the process is in place as well, so that you're not generating garbage input data. That's a lot of data engineering work. And of course, in the end, when your model is pushed into production, you're going to have a serving infrastructure. This is where software engineers or ML engineer who have software engineering background, who's going to build APIs, and you have to scale and maintain API as well. So it's a huge, effort, teamwork, and as an ML engineer, I think in some environment you might be focusing more on the model tuning side and training, and you probably need to use Spark and some other distributed system to scale your modeling effort. But in some other environment, the ML engineers work like ML ops as well. So you need to write, and software engineer as well. So you need to build, APIs, scale your model inference infrastructure, and also work on a little bit CI/CD as well. All right, so this is the MLOps process. Now, just to go through this again, the MLOps pipeline, right? It usually starts from data engineering, and then we move on to something I call the model engineering, and then software engineering, which is related to building the APIs and serving inference, infrastructure, and then DevOps, right? On the data engineering side, I think data engineers need to do data labeling. Data scientists might need to be involved as well, right? Labeling your data and automate that process if you need to do that at scale. The job title doesn't have to be data engineer, but someone will need to do it. I consider that as part of the data engineering effort. If you work with SageMaker or Mechanical Turk services to label your data at scale, you definitely are going to be working with the API. You want to automate that. There's no way you can just upload a CSV file and sit in front of a computer and just wait for that to finish. Definitely something you need to automate. And then data preparation, automating data pipelines, right? Ingesting data into the feature store. I think these are data engineering effort, right? And also control the quality of the data. Machine learning engineers will work on the model engineering side. That's data scientists and ML engineers. So they will be doing feature engineering. And of course, if you are building deep learning, and I think deep learning, a lot of the architecture is basically a massive feature engineering effort, right? Building transformers and things like that. But a lot of the ML models in production are actually dealing with structured data. So feature engineering is still required, right? And it's very important as well. So there's the scalable model training, right? Model evaluation, tuning, experiment tracking. I consider these as model engineering and also the model packaging. On the software engineering side, Model serving, right? Building APIs and endpoints, and figure out how to make sure your model prediction, is low latency and it's scalable. Model testing, unit testing, right? Integration testing, and on infrastructure side, that's DevOps, right? How do we build and maintain a Kubernetes cluster using kubeflow, or just using Docker containers and deploy that into Lambda functions or ECS? Pipeline automation, right? And also model and data version control. And of course, the ML engineers need to understand that as well. And CI/CD pipeline, deployment strategy, is it blue and green strategy or some other strategy? I think DevOps is important as well, right? And also building a more robust monitoring system. From a tooling perspective, it could be quite overwhelming. There's so many different options out there. So I'm just, was inspired by a blog post, but I just recreated this using some of the AWS services here. And I separate them into data engineering, ML, model engineering, software engineering, and DevOps. This, I guess, just has a little bit more detail, but idea is the same, right? So we talked about data labeling. We can use SageMaker for modeling, Labelbox, Scale.ai. I think they help OpenAI to label a lot of the data, but these services must be quite expensive, right? And then building feature store. There are different tools, SageMaker, and Databricks has some sort of feature store as well, right? But if you look at the data engineering side, right? Streaming data ingestion, maybe using Lakehouse or using a Snowflake data warehouse. I think data engineers will need to know this very well. Data quality control, right? Governance, metadata management. All of these are, very important data engineering topic. And Great Expectation is such a great package. You should definitely consider, right? That helps you, do testing and tell you if your data set is has good quality, and it will try to find issues in your data. For data processing and data queries, then you can use different tools. In some companies, if they use modern data stack, then it will be dbt in writing SQL queries, running them in Snowflake. A lot of the feature engineering stuff can actually be done in SQL because it's just more scalable, right? And it's running in more powerful data warehouse engines. But companies can use Apache Spark as well. If you have really tiny data set, you can work with pandas. So there are different options for data engineering. Now, after the feature has been, created, model engineer or ML engineers will basically move on to the model exploration and training evaluation stage, right? I think this is where, data scientists spend most of the time, right? So there's the Ray, which is something that's really cool, right? SageMaker, TensorFlow, PyTorch, and FastAI as well, right? And scikit-learn is probably the most classic one. And on the tuning side, there are a lot of options, weights and biases, hyperopt, and when it comes to model packaging, MLflow has the packaging capability, but and Onyx is a great language agnostic model packaging format, which is something I would really recommend for deep learning models. And for experiment tracking, there are also a lot of options. SageMaker has this, Databricks has the MLflow, which is open source, and there's weights and biases, and kubeflow has experimentation features as well. We probably also care about model and data version control. So DVC can be used for this purpose, and MLflow. There are different kind of model registry tools out there, right? I think when you learn machine learning engineer in MLOps, the tool itself is less important, but the concept is definitely more important. And different companies will be using different tools, but at least you need to know why you're using these tools, right? On the software engineering side, and I think any ML engineers, I think need to get comfortable with writing some basic APIs, right? Whether it's using Flask, and probably Fast API is better. And there are existing platforms such as Seldom, Kubeflow or SageMaker that allows you to deploy models easily. So you don't have to write a lot of lines of code. There's of course the Torch serve and TensorFlow serve as well. You need to be comfortable with writing better code, right, and well-tested code as well, and get comfortable with code review, right, and working with the proper IDE instead of just using Jupyter Notebook. But if you're like Jeremy, Howard, like you firmly believe in Jupyter Notebook, then you can just stick with MBDev, which is something which is really awesome, right? A lot of fast API applications are actually built using built on top of Jupyter Notebook. But I think a lot of the software engineers may not be very used to this approach. But if you love Jupyter Notebook, you should pick it up. And it's pretty awesome. It's going to translate your code into and help you, deploy that. On the DevOps side, if you start to work on, DevOps, then you're opening another can of worms. There's so many different concepts and so many different options of tools. But I think in a nutshell, at the very bare minimum, I think you need to get yourself familiar with Docker containers, one of the cloud platforms, and serverless functions. I think these are very popular nowadays. You'll definitely need to train and deploy models using Docker containers, and get familiar with AWS Lambda or similar, services in Google Cloud or in Microsoft Azure. Knowing a little bit about CI/CD, GitHub Actions, or Jenkins, I would probably recommend GitHub Actions, but it depends on your company as well. And then the version control, workflow automation. Apache Airflow is well known for automating or orchestrating data pipelines. It's used by some companies for automating their ML workflow, but it was not originally created for automating ML workflow. So there are some other options out there as well, but automation is definitely important in ML engineering as well. Okay, so I think I pretty much covered everything I want to cover. And then in the last few slides, I would like to introduce how WeCloudData, the approach that we take to teach our ML ops and machine learning engineering bootcamp. So again, we break this down to 4 different areas, right? Working as an ML engineer, sometimes for some companies you probably just need to focus on model engineering. But if you would like to take a boot camp and just learn this in a more comprehensive way, I think it would be great if the curriculum can touch on all of these, right? So you become more well-rounded. On the data engineering side, and of course, the way we teach this is that it will be very confusing if we, lecture by lecture, we're teaching new tools every week. It's very hard to teach, and it's very hard for students to absorb all of these concepts, and and it's incredibly hard for people to put everything together and make something work. So we take an iterative approach. So in the first few weeks of MLOps, which is in the second semester, the focus is more on just building the foundations, right? So there will be reviews of machine learning, and we focus on teaching ML pipelines, right? And also writing your custom transformers in Python. And you need to get familiar with object-oriented processing, right? OOP in programming in Python, working with VS Code, project packaging, and how to do, you work with GitHub and unit testing. And a lot of these are actually in the pre-boot camp, right? And on the DevOps side, we cover how to work with Docker and introduce, AWS. The focus is on AWS. So after you've learned all of these foundations, you're ready to move on to the novice level, which is just, training machine learning models and work with basic model packaging. So you can package a model and deploy that in a Flask or Fast API, to create a model serving and packaging using Flask. And we teach SageMaker as well, right? So at the end of the first couple of weeks, you will know how to deploy models in a Docker container and run that in AWS. right? Most of the online tutorials I've seen are basically at this level. But after you get comfortable with the entire process, I think it's time to move on to the more competent level. You probably want to automate the work, a workflow orchestration of your data pipelines, right? You start to do experimentation trackings, which means you want to learn how to deploy MLflow, either in Databricks or on your local containers. You're going to do large-scale model training and tuning using SageMaker or similar tools. And then on the model serving side, working with TF serving or KF serving. And at this point, you would like to learn how to deploy your containerized Fast API or Flask app in AWS using Fargate or ECS, which are container services, right? And this is the time you're going to learn how to use GitHub Action or Jenkins to do CI/CD pipeline as well. Okay, I think after this, you probably are ready to start applying for ML engineering jobs. And then we move on to the more experienced section where you start to learn more about data version control, model versioning with DVC, because one of the challenges with GitHub is that you can't have really large files committed to GitHub, right? So DVC is GitHub has there's an option in GitHub you can do that, but DVC is created for large files, right, and large models as well. So we can use DVC for model version control and work with MLflow as well. And then also model serving using Lambda and building API gateways. And this is the couple of weeks that we introduced model monitoring in production as well. And the last stage is, how do we take this and scale the infrastructure, right? This is where we're going to introduce feature store and teach students how to. So this is where we're going to introduce a little bit Kubernetes, but it's not a DevOps course, right? The goal is for you to be able to work with Kubeflow so you can deploy ML pipelines in a Kubernetes cluster. And also we cover more different ways of model serving. Yeah, so that's the approach we take to teach MLOps and machine learning engineering bootcamp. MLOps is the second semester, and the first semester we focus more on the model engineering side. So we cover PyTorch, deep learning essentials, and of course natural language processing and computer vision. So in total, students will need to complete 3 portfolio projects within 6 months. All right, skipping some of these details. I think I briefly introduced WeCloudData's bootcamp at the very beginning. So we have a pre-bootcamp if you currently don't have machine learning experience. So I don't think you'll be able to keep up if you haven't done any machine learning or scikit-learn in the past. So definitely need to get prepared. There's an admission test you need to pass. But if you don't have that background, we would recommend courses, and we have free pre-bootcamp training material that we can put you through. And then you join the bootcamp, learn for 6 months, work on portfolio projects, and there's an option for students to work with us on real client projects to beef up the experience portion of your resume, right? And then we provide the one-on-one career mentoring. You will be assigned a mentor who work in the industry to support your job search journey. Okay. All right. So I think that's pretty much it. We're at the end of this presentation. I hope you find this session useful. If you have any questions, feel free to let me know. I think we have some time left. I'm happy to address your questions. The recorded video, it will be uploaded to YouTube. So you can go to, I believe, youtube.com at WeCloudData. There's a question from Jason. What do you use for model security? That's a good question. Model security is actually not part of the curriculum yet at this point. Yeah. But I think it's a good idea to add that to the curriculum. Yeah. Any other questions? Do you provide licenses to softwares used? I think most of these software we use are open source, like PyTorch, PyTorch, um, and Jupyter Notebook. All the environment that you use are most of them are open source. But if you work with a cloud infrastructure, for model training we use Google Colab for labs. But when you work on the MLOps part, we cover Amazon Web Services and Docker containers for learning purpose. You can do that on your computer as well. It's only when you want to deploy the models in the cloud that's going to incur some cost, but it's not going to be a lot of cost. Probably within $100, you should be able to complete the program. What is a typical ML tech stack? It depends on the program language first, but I would say Python is pretty popular for most of the machine learning team. So if you look at this slide, this slide here, it covers most of the. Oh, let me find it. Here. Yeah. So a typical ML tech stack, it really depends on the company and team. For model feature store, I've seen a lot of companies using Airflow for automating their data pipeline. And then the features can be stored either in a data warehouse, right, such as Snowflake, Redshift. And a lot of companies also, there's batch jobs that generates the feature and save them just in Amazon S3 as object data. If you have real-time serving, you may want to consider a feature store or even just write the features into a NoSQL database. So it really depends on the company, the infrastructure the company use. Right? For modeling, most of the time, I think data scientists will be using scikit-learn, Python, PyTorch, and TensorFlow for model training. MLflow is pretty popular for model monitoring and also, sorry, for model experimentation, keeping track of your model experimentation. For model packaging, I've seen a lot of people just saving the model in a traditional Python format if they have small applications. But Onyx is becoming more popular. I definitely recommend Onyx for model packaging. And for serving, there are so many different options. Some companies, depending on the applications and backend, they may want to save, for example, save your Python model in Onyx, and you can use Java to rewrite your model serving code. Or if it's a data science team that doesn't have a lot of software engineers, they may actually just want to leverage, Fast API or SageMaker to deploy the model as an endpoint. But it probably doesn't meet the requirement for some projects because it needs to be very scalable, but also cost is a consideration. So yeah, what tool you're going to use ultimately really depends on the constraints you're working with, the latency requirement, how scalable that needs to be. And if your application is not that scalable, or if you don't even have the real-time serving needs, then you can just use Airflow to automate the batch model prediction and write the data back to a relational database on a daily basis. That's quite common as well, especially for some of those marketing models, because you don't really need real-time prediction. So it depends on the industry and the use cases. Would you know what industry currently has more of a demand for machine learning engineer? Banking, tech, government? I would say banks definitely have strong need for machine learning engineers. And a lot of banks are moving to the cloud, and they're trying to figure out the best way to deploy their machine learning models. But I think in the banks, a lot of the model prediction just needs to be batch prediction is probably enough for most of their models. But every bank, I think, will have teams that are exploring MLOps, model deployment. And then, but when it comes to fraud models, fraud prevention, credit scoring, that's when you're going to actually deploy the models in a more real-time fashion. And in the banks, I think traditionally there will be software team, right? Because in the backend, banks are more likely to use the Java stack. So you may want to export your model into the Java format or use a more generic format, and it will still be deployed into the more monolithic, backend